We've got some of the preliminary terminology out of the way from the first chapter. And now we're going to start in this section, this chapter I'm calling logic. Now, the logic deals with reasoning and techniques for reasoning. And geometry is usually the vehicle that we use to teach those concepts. Now, logic is not just for geometry. It's not just part of the geometry. It's part of a lot of mathematics. In fact, there's a whole discipline of mathematics just that focuses on logic. But we use geometry as a vehicle for exploring logic as an introduction. So, to start off with just some terminology, we're going to talk about conjectures. A conjecture is an unproven statement based on observation. So you see something and you think, I can make a conjecture about this. For example, if you see just something simple, if you see someone walking toward a door, you could conjecture, I bet they're going to go out that door. I bet they're leaving. That's a conjecture. You don't know for sure. It's not proven. But the fact that they're walking toward the door, you're thinking, I think they're probably leaving. I don't think they're going to walk over the door and then just turn around and come back. Okay, so that's kind of a just a simple example of conjecture. Now, what we're going to use is we're going to use those conjectures to engage in inductive reasoning. And inductive reasoning is when you form a pattern, you find a pattern in a specific set of cases, and you conjecture about the general case. Now, I've got an example here to show you. There are these things called triangular numbers, and I've listed them here. And you can see the first triangular number is 1. So it goes like this: 1, 3, 6, 10. Say 1, 3, 6, 10. And it goes on and on. But I've just listed 4 of the triangular numbers here. Now, what we want to do is I want to use this to explore how we observe a pattern and make a conjecture. Now, these triangular numbers are formed by putting dots. So we start off with 1 dot. Here's 1 dot right there. And we want to add some dots to make a triangle out of it. So I've got this dot and I put 2 down here. Okay. So I've got 1, 2, 3. And now you can see that kind of makes a triangle. Okay. So we say, okay, I added 3 dots to that. That makes a triangle. Then, okay, now look over here. We've got these 3 dots from the previous. And now I want to make a triangle out of that. So between these 2 dots, I'll put a dot. And then dots on either side to kind of complete the triangle. So now notice we've got a triangle here as well. And if you look at this, this is 6 dots now. So we've got these numbers 1, 3, and 6. Now I want to go for the next one. So notice I've got these ones that I just, let me mark. I've got these ones from the previous, right? And then I want to go to the next step there. So I'll add between this dot and this dot, I'll add a dot. Between this dot and this dot, I'll add a dot, and then 2 on the outside. So you see the pattern, see what I'm doing. Between every pair of dots on the horizontal there, I'm putting a dot in there, okay? And we get this new triangle, and notice there are 10 dots here. So we've got this. We go 1 to 3 to 6 to 10. Now, so T1 equals 1, T2 equals 3, T3 equals 6, and T4 equals 10. And you might say, okay, well, what is T5? If I go the next step up, you could make a conjecture. Okay, so you make an observation about a pattern, and then you make a conjecture about the more general case. In this case, well, what would be the 5th triangular number? Okay, so notice we added 2 to get to the 3. We added 3 to get to the 6. We added 4 to get to the 10. I bet we're going to add 5 to get to this one. So that's going to be 15. That's what my conjecture would be. So we could kind of try out that conjecture. Let me pick another color here, and I'll just add on to this one up here. So we want to look at T5, so I'm going to, between each one of these, I add a dot and then a dot on the outside. And it looks like, I've added 5 dots there. So yeah, so we conjectured about the next thing coming. Observing the pattern, we say, okay, the next thing we're going to observe is going to be 15. So T5 is 15. Now, so there we were able to conjecture about the next term. Now, you could say, okay, well, that's not enough. I want to see if I can figure out, well, what is generally? In other words, what if I want the nth triangular number, maybe the 100th or whatever? Well, we need to take a look at that. So let's see if we can figure it out. Now, I try to note a pattern here: 1, 3, 6, 10, and 15. And I want to try out I'm going to conjecture. I'm going to make a conjecture now. I'm going to conjecture that n times n plus 1 over 2. I'm thinking that will be the nth triangular number. So let's see if it works. When n is 1, we've got 1 plus 1 over 2, and that's T1, and that does equal 1, right? This cancels. Now let's try when the triangular number is 2. So we've got 2 times 2 plus 1 over 2. Ooh, that's 3. Woo, look at that. Now let's try the third one. This is going to be 3 times 3 plus 1 over 2. And that is 3 times 4 over 2. Ooh, that's 6. Hot dog. It's working so far. Let's try the fourth one. We would have 4 times 4 plus 1 over 2. And that's 2 times 5, 10. It looks like it might be working. In other words, I'm thinking that, now I've not proven it, but this is my conjecture. I'm saying that the nth triangular number can be given by n times n plus 1 over 2. Okay, now let's look at another one. Let's suppose we've got a situation like this. Let's just suppose we are multiplying 2 times 1. And we know that that's going to be 2. And then let's go 1 times 1. Well, actually, let me back it up a little bit. Let's start up here. Let's say we've got 4 times 1. Of course, that's 4. 3 times 1 is 3. Okay. 2 times 1 is 2. 1 times 1. Let's go that way. 1 times 1 is 1. And 0 times 1 is 0. Now notice, look at this pattern. 4 times 1, 3 times 1, 2 times 1. We keep subtracting 1. We see a pattern here. We see that we're every time decreasing by 1. 4, 3, 2, 1, 0. What would be the next number? Well, -1, right? So we've got 4, 3, 2, 1, 0, -1 times 1. And then -2 times 1. Now, you look at this pattern and you could conjecture that, I notice when I multiply 2 positives together, I get a positive. And when I multiply a negative and a positive together, I get a negative. So based on this, it seems pretty obvious that you could conjecture that a negative times a positive is a negative, because you look at the pattern and you can conjecture. Now let's suppose that we've got this. Let's suppose that we've got 4 times -1. Well, that's -4, just based on what we've just did. And then let's do 3 times -1. Well, that's -3. Okay. 2 times -1. Well, that's -2. 1 times negative 1, that's negative 1. 0 times negative 1 is 0. Now, the next thing we multiply is negative 1 times negative 1. And the next number in this pattern is going to be a positive 1. Ah, so we kind of note this pattern that when we multiply two negatives together, we get a positive. Okay? Yeah, that's it. So that's the way we can use patterns. Okay, now, what I want to do next, there's another term, a counterexample. When we talk about a counterexample, here's the way we use it. You can have a conjecture. You can say, you can make a conjecture, and then you can prove that conjecture wrong with just one counterexample. Like if you have a conjecture, let's suppose you attend a basketball game, and you notice every student you see is above 6 foot tall because they're on the basketball team. So you might conjecture that everyone that attends that school is above 6 feet tall. That's your conjecture based on viewing the basketball team. And then someone brings a student forward that's only 5'8", and says, this student attends that school and they're only 5'8". That's a counterexample. And they've proven your conjecture wrong. Now, I've got a couple here in math. Let's suppose that we conjecture that the square root of x squared is equal to x. Well, that's true a lot of times. If x is equal to 2, 2 squared, the square root of that is equal to 2. But let's suppose, here's a counterexample. Let's suppose that x is equal to negative 2. Okay, let's see if this works. The square root of negative 2 squared is equal to the square root of 4, which is equal to 2. Ah, that's a counterexample. So it turns out that the square root of x squared does not necessarily equal x. We use this counterexample to show it's wrong. The fact is, here's what you need to remember. This is the square root of x squared equals the absolute value of x. It's only equal to x if x is 0 or bigger. So we had a counterexample there. Okay? So if x is negative 2, well, the square root of negative 2 squared does not equal negative 2. Okay, now let's look at this one. The square root of a squared plus b squared equals a plus b. Okay? Well, let's see if that's true. Let's look at a counterexample. Let's let a equal 3, and let's let b equal 4. So let's see here. 3 squared plus 4 squared is equal to, well, 9 plus 16, that's 25. Square root of 25 is 5. Okay? Now, let's see if 3 plus 4 is equal to 5. See, 3 plus 4 is equal to 7. Ooh, not 5. Those are not equal. So this is an example of, I used a counterexample to show that the square root of a squared plus b squared is not a plus b. Okay, so I've got a couple of problems down here for you to work with the assignment.